Welcome to One Chemistry. In this video, we are going to see Curtius rearrangement reaction. We will see many examples, particularly 22 fully solved examples from various examinations. Stay tuned. What is inside this video? At first, we are going to see what is Curtius rearrangement and mechanism behind Curtius rearrangement. The discussion include basics, which is chiral carbon and cyclic system involved in the rearrangement, and notes on starting material and product variation. Very important thing is we are going to see 22 fully solved examples from various examination. They are completely solved as much as I can, so utilize the PYQs. At first, we will see what is Curtius rearrangement. It's a rearrangement of azide to amine. Acyl acid is the starting material. If you are heating it up, N2 elimination happen. You have isocyanate. Then it is converted to amine by various process. This reaction involves CO and N2 removal. So starting material and product differ in one carbon less. Heat or light can be a catalyst in the present situation. The fundamental facts about this rearrangement is the product will be one carbon less. The mechanism is concerted. Sometimes non-concerted mechanism also observed. The third fact is retention of configuration happen if the migrating group is the chiral carbon. Then we are going to see the mechanism, how azide converted into amine. Azide is the starting material. If you redraw nicely with nitrogens, you have nitrogen with positive and negative charge and one neutral nitrogen. Nitrogen is the good leaving group because it has triple bond, very strong bond. So it leaves itself, act as a leaving group. For that we have to redraw the molecule with N triple bond. Then keep the positive and negative charges. Then nitrogen elimination leads to the nitrene. Nitrene is the nitrogen analog of carbene. So nitrene form. Nitrene is highly unstable. To quench the nitrene, R group migrates, form isocyanate. Here flow of electron happen in same nitrogen. One bond form, two bonds form at the same time. One is double bond, one is R nitrogen bond. If you read down nicely, you can clearly see isocyanate. Then if you add water, you have H and OH addition to the carbon nitrogen bond. Then too many heteroatom and the carbon is unstable. So CO2 elimination occur, you end up with amine. So you start from acyl acid, end up with amine with one carbon less. Here important thing you should note here is intermediate is nitrene as well as isocyanate. Then the next basics, migrating group chirality. If migrating group is the chiral group, the configuration is retained. If you start with S configuration, the product also end with S configuration. So there is no change in the chiral center, no change in the chiral carbon. This is the one kind of proof for concerted mechanism. So if you start from S, you end up with S. That is called retention of configuration. The starting material azide can be prepared from many ways. With acid, if you use SOCl2 NaN3 or PCl5 NaN3 mean you end up with acyl acide. In the same way, if you use acid chloride with NaN3, you end up with acyl acide. The interesting fact is if you start with ester reacting with hydrogen and nitrous acid mean you end up with acide. Then if you start with anhydride reacting with sodium acyl you end up with acyl acide. Then if you use DPPA with acid, DPPA is the acid which is diphenyl phosphoryl acid. It converts acyl acide. So 5 kind of different starting material known. Definitely many more. Here I given prominent one. Then regular rearrangement happen. You end up with amine there. Then the same way many types of products are possible. Once the acid is converted into isocyanate by nitrogen elimination, it can be converted into many products. If you add H2O, that is we shown in mechanism, you end up with amine. H2O added to the CN bond HOH. Since carbon has many heteroatom, it is unstable, so leave a CO2, end up with amine. If you use alcohol, it's simple addition reaction with carbon and nitrogen. You end up with ester with amine. Then if you use amine, you end up with urea derivative. So you can tune the products from three different reagents. One is water, alcohol or amine, or any nucleophile can form the product. Depends on the reaction condition. Then we are going into second section, which is 22 fully solved examples. Why so many examples mean problems are best way to learn. It will give you different perspective, different understanding. Most importantly, complete perception. It will give you confidence while solving the problems. So solve every problem individually. Make use of it. Let us see the first example. If you use benzoic acid, you are using SOCl2, sodium azide, heating it up, and methylamine you are using. You should find what will be the final product. Here benzoic acid you are using. The reagent is SOCl2. Hence OH becomes Cl since it is a chlorine donor. So acid become acid chloride. Then you are using sodium acid which converts chlorine into acid. So acid chloride become acyl acid. Then you are heating it up. So chances of Curtius rearrangement. Here N2 elimination is the first step. N2 eliminates by the migration of phenyl. So phenyl migrates, N2 eliminate, it form isocyanate. If you redraw nicely, you can clearly see isocyanate structure. Then you are adding the amine. Amine will add to carbon and nitrogen bond. You end up with urea derivative. Here you are tuning the product into the required product, which is the urea derivative. The concept you have to learn here is you should master the acid formation because Curtius rearrangement can be a part of the total synthesis. Then the next example, you are using the acid chloride which is in the phenyl form. You are using sodium azide, acid hydrolysis, heating it up. You should find what will be the final product. Here the reaction have different starting material. Obviously we have to find acid pathway. The starting material is acid chloride. You are using sodium azide mean chlorine converted into N3. It's a functional group reaction. If you redraw with nitrogen, because next step is nitrogen elimination, instead of creating N triple bond, draw the N3 with triple bond. So you have positive negative nitrogen. N2 leaving is easy. N2 leaves, you have nitrogen formation. So the usual mechanistic pathway, phenyl group migrate, you have N double bond C formation. So N double bond C forms. So if you look at it clearly, it's isocyanate reaction. So isocyanate is formed. Then water you are adding, H2O addition happen. Then heating promote the CO2 elimination. You end up with amine there. So starting with acid chloride, end up with amine. It's an important functional group conversion reaction with one carbon less. The starting material has 7 carbon atom, product has 6 carbon atom. You end up with aniline there. The concept you have to learn here is you should master the functional group conversion to master the rearrangement reaction. Then the next example, here you have chiral carbon, acid chloride above the plane, which is solid wedge, hydrogen below the plane, which is dotted wedge. You have methyl and ethyl on the plane. You are using sodium azide, base and heating it up. You should find what will be the final product. Here acid chloride is there, acyl acide you are using. The chloride converted into acid there. It's a functional group conversion. Chlorine to acid formation. Then you have acid mean the chances of Curtius rearrangement, that is N2 elimination. The N2 elimination leads to the nitrene formation. Nitrene is like radical, so chiral carbon should migrate. So the chiral carbon migrates above the plane to above the plane migration. Migration happened. You have isocyanate above the plane. Isocyanate is unstable. If you add water mean H and OH add in the CN bond, which leads to the CO2 elimination. Many heteroatom in the carbon is unstable. CO2 eliminates. You end up with amine. This problem is interesting because starting material stay with the same configuration as the product. So the retention of configuration happen. So in the Curtius rearrangement, no change in the chiral center. Then the next example, you have pyridine, side chain, you have acyl acide, you are heating it up, water you are using, you should find what will be the final product. Here acide is there, so chances of Curtius rearrangement. First step will be N2 elimination because heat you are using. Nitrogen is the good leaving group. So N2 leads to the nitrene formation. Sudden loss of two bonds create the nitrene in the same nitrogen. The nitrene is unstable like radical, so it has to be quenched. So pyridine ring moves. You have isocyanate. If you redraw nicely, you can clearly see isocyanate formation. Then H2O adds. You have H and OH addition in the NC bond. Then heating leads to the amine formation. Here, the carbon dioxide elimination is possible because many heteroatoms in the carbon. The concept we outline here is even heterocycles can undergo Curtius rearrangement. Here, pyridine migrates, form the Curtius rearrangement. Then the next example. Here you have carbonyl. One side you have azide, another side you have benzyl. You are heating it up. Then water you are using. You should find what will be the final product. Here azide is there. Heating condition mean Curtius rearrangement. First step is obvious. N2 elimination because N2 is the good leaving group. It leads to the nitrene formation. Nitrene is like radical. So opposite group to migrate to quench the nitrene. It migrates. You have new NCO bond formation. So whole benzyl group migrates, form isocyanate. Then you are adding the water. Water adds to the carbon and nitrogen bond, form the acid with amine there. There are many heteroatom on the carbon. So heating leads to the CO2 elimination. You end up with amine. Here starting material you have two carbon at the side chain. Here only one carbon atom. It is the benzyl amine as the product. So the concept we outline here is in Curtius rearrangement, always one carbon less even with the side chain. Then the next example, you have carbonyl. One side you have phenyl, another side you have azide. You are heating it up. Water you are using. You should find what will be the final product. Here Curtius rearrangement happen because acide is there, you are heating. First step will be N2 elimination. The same story here. N2 elimination leads to the nitrene, which is highly unstable. It has to be quenched. So phenyl group migrates, form new NCO bond. If you redraw nicely, you can clearly see its isocyanate formation, which is NCO bond. Then water addition leads to the addition reaction in carbon and nitrogen bond. Further heating condition leads to the CO2 removal. The CO2 removal is possible because of many heteroatoms on the carbon. Then the next example. Here you have binaptyl system. Beta position you have acyl acide as well as O-methyl group. You are heating it up. Water you are using. You should find what will be the final product. Here acid you are using as the starting material, heating it up. So chances of Curtius rearrangement, first step will be N2 elimination because N2 is the good leaving group. It leaves form the nitrine. Then nitrine has to be quenched. For that whole group migrates, that is binaptyl group. It migrates, form NCO bond. If you redraw nicely, you have NCO bond at the linear way. Then water add to the carbonyl and nitrogen through the addition reaction. So NH-COH bond is formed. Then heating leads to the CO2 removal because of many heteroatoms on the carbon. So CO2 eliminates, we end up with simple amine. Then the next example. Here you have Fischer projection of the chiral carbon. Hydrogen, ethyl, methyl is there and acyl acide attached with it. You are heating it up. Water you are using. You should find what will be the final product. The starting metal is chiral carbon with R configuration. Since hydrogen is the horizontal bond which is above the plane, real configuration is reverse. The analysis gives yes, since hydrogen is above, so you end up with R configuration. The compound has azide and you are heating it up. So chances of Curtius rearrangement, first step will be heating. Heating leads to the removal of nitrogen, which form nitrine there. Nitrine is the very unstable intermediate. To quench the nitrine, chiral carbon migrates. You have new NC bond. So the migration happened. This is the rearrangement step. If you redraw nicely, you can clearly see isocyanate formation. Cyanate means CNO, isocyanate means NCO. Here NCO form. Then you are adding the water. Water leads to the addition reaction in the carbon nitrogen double bond, which leads to the H and OH. Then you are heating it up. You end up with CO2 removal because of same reason that carbon attached with many heteroatoms. The important thing is you are not changing the configuration, that is R configuration. So the starting material is R configuration, product also R configuration. That suggests that Curtius rearrangement don't change the chiral carbon, retention of configuration happen. Then the next example. Here you have acyl acide attached with cyclopropane. You are heating it up. Water you are using. You should find what will be the final product. Here azide is the heating condition you are using. So Curtius rearrangement. What is special about this reaction? The starting material has full ring. Whether it is open or not is the real question. So acide is there. Another side cyclopropane is there. Heating you are using mean N2 elimination. N2 elimination leads to the nitrine formation. Nitrine is highly unstable, so it has to be quenched. So cyclopropyl group migrates. You have new CN bond. At the same time, carbon and nitrogen double bond also form. So it's a isocyanate formation. If you redraw nicely, you can clearly see isocyanate, that is NCO bond formation. Then you are using the water. Water attack the carbon and nitrogen double bond. End up with addition reaction. Here carbon contain oxygen, hydroxy group and nitrogen. It's highly unstable because carbon attached with many heteroatom. So CO2 removal happen. You end up with amine. Here ring is not open because the mechanism is concerted. So the ring is not open. The concept you outline here is in Curtius rearrangement, strainful rings not open like Wagner-Merwin rearrangements. Then the next example. Here you have acid chloride, sodium acide you are using, then benzyl alcohol as the next reagent, heating it up. You should find what will be the final product. Here acid chloride is there. You are using acyl acide. So Cl converted into acide there. Acide with 3 nitrogen. Nitrogen is the good leaving group. So N2 leaves, it form nitrines. Here nitrine step not shown because of bulky reactant and product. So nitrogen elimination and migration shown as a single step. So vinyl migrates, nitrogen leaves. You have new nitrogen carbon bond as well as carbon double bond. Then next step you are using the benzyl alcohol. So new kind of starting material. You can simplify it like ROH. Here H and benzyl oxygen addition happen. You end up with final product. The whole question is about, can sp2 carbon migrate? Can sp2 carbon bond breaks? Yes, it is possible. Because of nitrine instability, the reaction happen. You end up with final product. You end up with final product. Then the next example. Here you have cyclopropane, the 2-methyl group, allyl group. The reagents are phosphoroxy acid, tertiary butyl alcohol, and triethylamine. You should find what will be the final product. Here acid you are using phosphorus acid can donate the acid group. So basically the functional group conversion, the OH from acid leaves, it converted into N3 form. Here the chiral carbon don't change its configuration because the mechanism is concerted. So N2 carbon leaves, you have migration of cyclopropyl group. Here cyclopropyl group is the chiral carbon specified compound. The carbon specification don't change. Since migrating group is below the plane, the reaction happen also below the plane without change in the chirality. Then N2 eliminates. Because of the N2 elimination, migration leads to the isocyanate formation. Then tertiary butyl alcohol adds. You have new CO bond and new hydrogen bond. It is a kind of production of amine there. You end up with NHBOC. The concept you have to learn here is even the migration happen on the same plane as well as the chiral carbon don't change in the configuration. This reaction is very important. It proves the nature of concerted mechanism. Then the next example. You have bicyclic compound with ketone and acid, 2-methyl groups. It's a conversion reaction. The first reagent is SOCl2, second reagent is NaN3 methyl alcohol, third is tertiary butoxide, then acid hydrolysis. You should find what will be the final product. Here acid is the first reagent is SOCl2. It's a functional group conversion reaction. OH becomes Cl, that is acid become acid chloride. Then you are using NaN3. It's a functional group conversion. Chlorine to azide. Once azide form, the possibility of Curtius rearrangement. Azide has N3, so nitrogen is the good leaving group. The group migrates. You have new NCO bond. The NCO is isocyanate. Here it has the possibility of many sideways reaction. First it will be abstraction of proton by base. It abstract. You have anion. Then the anion can attack the CO. You have new CC bond. As it attacks, anion form in ring opening reaction to balance the carbon valency. Bicyclic compound become fused compound. Here stereochemistry is preserved. You have to know which is above the plane, which is below the plane. Here as it is below the plane mean all methyl are above the plane. That's what specified here. You can write in another way also. Acid above the plane mean methyl below the plane. This reaction may look complicated, but Curtius rearrangement can be a part of larger organic conversion reaction. Then the next reaction, you have benzene. Acyl acide is there, then amine also there. You are heating it up. You should find what will be the final product. Here acyl acide is there. You are heating in Curtius rearrangement. First step will be removal of nitrogen. Nitrogen removed. It forms nitrine. Technically it is called acyl nitrine. It is highly unstable. So it has to be quant. So benzene group migrate, you have new NC bond, CN double bond also form, which leads to the isocyanate, which is NCO. Here you have internal nucleophile because amine has lone pair of electron. It can attack, form the cyclization. Cyclic products are more stable. So cyclization promote the reaction here. It's a intramolecular first step formed with heterocyclic ring. Then the next reaction, you have cyclohexanone, phenyl acid you are using, trifluoroacidic acid as the reagent. You should find what will be the final product. Here cyclohexanone is the starting material, acyl as the reagent. So first step will be acide formation from CO. It's a nucleophilic addition reaction with O minus. Later will become hydrogen from acetic acid. Since acide is there, you might expect Curtius rearrangement, but phenyl group is there, which is a new one here. So what really happened is the group migrate, you have N2 elimination. So N2 eliminates, nitrogen formation, conversion happen at the same step. It's a kind of partial rearrangement, but similar kind of Curtius rearrangement. So ring open, 6-member ring becomes 7-member ring. It forms cation near the alcohol, then cation has to be quant. So OH becomes CO there. The concept you have to learn here is there can be many quenching pathway. You have to decide based on the intermediate formation as well as stability of the intermediate. Then the next reaction, you have acetic acid, phosphoxyacide you are using, then tertiary butyl alcohol you are using. You should find what will be the final product. Here the answer will be simple, but you should know the reagents and its purpose. As it is there, phosphoxyacide you are using mean it take out the OH converted into N3, basically a functional group conversion of acid into azide. Then it will come under Curtius rearrangement. If you redraw the nitrogen, it can be easy to remove the N2 molecule, form the nitrogen there. As usual, nitrogen is unstable, so methyl group migrates, form isocyanate. Isocyanate can be rewritten in the clear way. It is rewritten. Then nucleophile H2O attacks. H2O form addition reaction with N and C. Then instead of water elimination, tertiary butyl alcohol can react with alcohol. OH can react with tertiary butyl alcohol, end up with ether there. The concept you have to learn here is you have to always follow the reagents as well as role of the reagent. Then the next example, here you have carbonate, one side acid, another side styrene with R groups. You are heating it up and using trifluoroacidic acid. You should find what will be the final product. Here starting material is tricky because phenyl is hidden here. If you redraw with phenyl and acid group, you may see possibility of Curtius rearrangement with cyclization. First step will be heating. Heating removes the N2 group, form the nitrogen there. Nitrogen is unstable, so sp2 carbon bond should be broken. So bond breaks, new NC bond as well as N double bond C bonds form. Here isocyanate is there. Acid you are using. So benzene can act as the nucleophile. It attacks, it forms new carbon-carbon bond. It's a kind of ortho substitution. Then after the bond formation, cation and anion is there. So aromatization is the highest priority. Hydrogen transfer end up with aromatic cyclic compound. Here starting material to product is unimaginable, but you have to redraw the molecule, follow the mechanism, follow the charge to identify the correct product. Then the next example, here you have indole, third position you have acyl acide with side chain, heating it up, acid you are using, you should find what will be the final product. Here heterocycle is there, acide at the side chain. So first we form the nitrene. So heating removes the N2 from N3, form the nitrene. As we discussed, nitrene is highly unstable. So the group migrates, form the isocyanate. Isocyanate should be redrawn for the cyclization. Like previous example, the cyclization is possible because of 6-member ring. Ring should be activated as well as carbonyl should be activated. Acid can do both the activation, new CC bond forms, then you have to regain the aromaticity. So hydrogen losses, you have indole with fused ring. Here cyclic amide fused with indole. The concept you have to learn here is in Curtius rearrangement, the aromatic ring comes in. The possibility of ring substitution always dominates. Then the next example, here you have bicyclic compound with ketone, acyl acide at the bridge, 2-methyl group, heat and tertiary beta oxide you are using. You should find what will be the final product. The similar example we already seen. We redraw the molecule for the Curtius rearrangement. So acide N3 bond written with positive and negative charges. If you are heating mean N2 eliminates, migrating group migrate, you have new NCO bond. If you redraw nicely, you have linear NCO. Then you are using the base subtract the proton. The anion attacks, you have new CC bond. Then OH again attacks, it opens the ring to compensate the valency. Bicyclic compound become fused system. Here the compound can be confusing, so I given numbers. If you read nicely, it will be a fused system with cyclic amide with acid side chain. This kind of examples may be complicated. You should be strong with fundamentals as well as functional group conversion reaction. Then the next reaction, you have acidic anhydride reacting with sodium azide and heating it up. You should find what will be the final product. Here anhydride is there. Anhydride has CH3COO minus as the leaving group. It is self-stabilizing due to resonance. So it is a good leaving group. So acide can attack. CH3COO minus can eliminate, form the acide. Basically, it's a functional group conversion, anhydrate to acide formation. Once the acide is formed, the possibility of Curtius rearrangement, you have to redraw with nitrogen. So N2 elimination happened, you have nitrene there. Nitrene is highly unstable. Only possibility is migration of methyl group, form the isocyanate. Since the bond angle is not correct, you should redraw the molecule to isocyanate, then attack with H2O, then reacts with H2O mean it form addition reaction with nitrogen and carbon, and heating leads to the CO2 elimination. As we discussed, carbon with many heteroatom leads to the CO2 removal, end up with amine. Here you just see starting metal is anhydride, product is amine, completely unusual, unexpected product. The concept you outline here is you should master the organic conversion before getting into any rearrangement reaction. Then the next reaction, you have benzene, side chain you have ester which is methyl ester, reacts with hydrogen, nitrous acid, heating it up. You should find what will be the final product. Here ester is there. OCH3 is the good leaving group. So hydrogen leads to the acyl hydrogen formation. CH3O minus leaves, NH2 bond forms. Then if you use HNO2, it converts hydrogen into acid. So the possibility of Curtius rearrangement. So you should redraw the molecule with nitrogen. Here N2 leaves, carbon migrates, new NCO bond, both exhibited in the same step, form isocyanate. Then you should redraw the molecule for the water addition. Water add with carbon and nitrogen leads to many heterocyclic atoms and carbon. So heating leads to the CO2 removal and NH2 formation. So starting metal is ester, product is amine with less number of carbons. So the concept you outlined here is ester functional group can be fully converted into amine through Curtius rearrangement. Then the next reaction. Here you have acid bromide with side alkyl group which is propane. You are using sodium azide and heating it up. You should find what will be the final product. Here bromine is there. You are using sodium azide mean it's a functional group conversion. Bromine converted into N3 by nucleophilic addition and Br elimination. Then acid is there. Possibility of Curtius rearrangement. So we redraw the molecule with nitrogen. Then do the rearrangement mean alkyl group migrates, N2 eliminates, form isocyanate. If you redraw the molecule for quick understanding, clear NCO bond is visible. Then the next reactant is water, which will undergo addition reaction with the NC bond. Further heating it up leads to the CO2 elimination. Here CO2 eliminates because of unstable carbon, because the carbon is attached with many heteroatom. It is highly unstable, leads to the final product. The concept is outlined here is functional group conversion of acid chloride into amine is possible through Curtius rearrangement. Here you have acidic ester with alpha cyanide. You are using hydrogen, nitrous acid, heating it up. Further acid hydrolysis. You should find what will be the final product. This example is very important because you are generating amino acid from the reactant. The Curtius rearrangement help for the conversion. We will see step by step. First step will be hydrogen addition. Hydrogen converts ester into acyl hydrogen. Then nitrous acid you are using. It converts hydrogen into acid. Then possibility of Curtius rearrangement. If you redraw nicely, you have acyl acide. Acide has N2 as the leaving group. So methylene cyanide migrates. Nitrogen leaves. You have nitrene formation. The Curtius rearrangement happened through methylene group migration. So methylene group migrates. You have isocyanate. Then water addition. Water addition leads to CO2 removal because of its instability. Form the amine. Then you are doing acid hydrolysis where cyanide becomes COOH, which is basically a amine with acid. It is the amino acid. The concept you outlined here is Curtius rearrangement plays the important role in the amino acid preparation. Then we will summarize what we learned. The Curtius rearrangement is the conversion of acyl acide into amine through the isocyanate formation. Here you should note that nitrene as the intermediate form. It is highly unstable like radical. The facts you should learn here is it's an intramolecular reaction most of the time, concerted. In few cases it is non-concerted, and very important thing is retention of chiral carbon happen. If chiral carbon migrate, it retains with one configuration. Then final product is tunable by different set of reagent. Final product is tunable based on your interest. Final fact is while doing mechanism, always look for cyclization and aromaticity.